Hey, so thank you for having me. The name of this talk is Code Without Keywords. I think this is like my third presentation at js.la. A little bit about myself. My name's Sam. Let's call me a computer scientist because that makes me sound way smarter than I am. I organize another meetup called Papers We Love that meets the night before js.la. We talk about computer science papers, and I do front-end esports stuff at Yahoo. So you've all done JavaScript, I assume. You've seen the new JavaScript. I've been doing JavaScript for probably about 7 years now. I've seen the number of reserved keywords kind of go up and down. Not all of these are currently reserved keywords in JavaScript, but a lot of them are. Some of them are historical. There are a lot of these, aren't there? There are a lot? Are there like too many? Does JavaScript have too many keywords now? Okay, because I'm like, keywords, new keywords, which ones do you even use? People are talking about var, let, some people talk about else. Do people use else? Okay, well, anyways, I think that we can do better. And so, when we talk about how many keywords does JavaScript have, we should talk about, like, why do we use them? Where do they come from? We see them in places like var a equals 1, let b equals hello, if hello, return 5. And so this comes from something that we call the Great Divorce, or I've heard other terms, but basically JavaScript, the designers separated statements from expressions. So when you say var a equals 1, you then have a variable, and that's an expression, and you have a value 1, and that's an expression, but the statement var a equals 1 doesn't actually have a value. That's undefined. And so, keywords like to appear in statements. If you think about like if, that's a keyword. Return, that doesn't have a value. That's a keyword. These are all statements. So let's not use them. So I'd like to go through kind of keyword by keyword and see how we can use fewer of them. So if we start with function, as you probably know, JavaScript ES6 added the fat arrow function. So where you would have had to say function add 3, return x plus 3, you can just skip the function, put the x in parentheses. And this is actually sort of a twofer, because if the body of your function is just an expression, you don't even need a return. And so you can just have add 3, x in parentheses, x plus 3. Var and let, you don't need them. And I'm not talking about const. How many of you know what let desugaring is? How many of you have ever heard the term let desugaring? I see a hand. It's a Lisp thing. When you let variables to declare them in a scope or in a block scope like you would with JavaScript, that is actually implemented in Lisp typically as a macro because it is not fundamental to the language. There's a technique where anytime you are declaring a variable, you can actually just wrap that whole thing in a function, and that is its own scope. And so anytime you'd have var a equals 15, var b, let c, you can just have an anonymous function, have 2 parameters, a and b. Those are accessible, and then pass 15 and 30. You're following me? We're all on the same page. OK, cool. So a little bit of a tangent, because I love tangents, and I'm terrible at segues. Yeah. So this is something I sort of discovered by accident with a coworker a few years ago, and we talked about it, and then we both kind of looked at each other and we joked like, oh yeah, you could do this, and then I looked it up, and you actually can do this. So this is a real thing, where you don't need variables to have data structures. You can have basically closures, and so we can declare like a fundamental data structure as a pair, which is actually a function that takes two values, returns a function that takes a function that takes two values. If you're confused by that, it'll be more obvious as we're going along. So basically, to create a pair, you would just call pair with two values. And then pairs, because they return functions, we should have two functions to pass into it. So we can have first and second. And so if you pass first, it'll always return the first parameter that's given. Second will always return the second. So you can take a pair, and you can create it, and then pass first or second, and that will return the value. You're all on the same page. OK, great. Because we're just going to keep digging deeper. This is pretty basic to this talk. So then if you know any Lisp, or you've heard of car, cons, cutter, basically we want to have a function that we can pass a pair rather than have the pair be the function that we pass anything else. So we can wrap that by saying car is a function that takes a pair and then applies that pair to first. And cutter takes a pair and applies it to second. And then we can just alias. And this is basically, you can build up a list of like 1, 2, 3, 4, 5, and then say, give me the second of the second of the first of the first, and it'll give you 3, or the first of the first of the second, and it'll give you a 3. Does that make sense? Mind blown? I thought that this was absolutely crazy when I first found out about this. So a quick aside on currying. If you don't know what currying is, basically instead of having a function that takes like 5 parameters, you just keep having nested functions, and they keep returning functions that take like 1 extra parameter. So basically, instead of having like pair A and B, you have pair A return a function that takes B that takes F. If that makes sense. We're going to be doing this notation a lot. So yeah, tangent number 2. If we're trying to eliminate if statements, it seems sort of difficult to remove control flow, right, from your programs. That's hard. But you can kind of think of branching as like a data structure, because you have a test, you have like do this first thing, and then you have do the second thing. In formal logic, we call it like the antecedent, the consequent, and an alternative. But it kind of looks like a pair, right? It's a pair of things, and then something that tells you which one to do. And so this is just that more verbosely. Test can be a function that returns the first or second part of a pair. And so true is like, car, and false is like cutter, and the pair is actually just is your program. So void is just useful. You'll see it again. It just takes an argument and passes it through and does nothing with it. And then you can see that true basically takes a consequent and alternative and invokes the consequent. False does the opposite. And then if takes a test, a consequent, and an alternative, and then passes those through. So if you say if as a function call, if true, and then 2 parameters, this worked, or if false, it'll return the second one. Is that crazy that you can do that? Okay, so okay, I'm moving on to numbers. At this point, you might say numbers aren't really a keyword. I know they aren't, but I'm having fun. So, but before we get to numbers, we're going on another tangent about P&O axioms. Do people know P&O axioms? Okay, well, I will explain them. Basically, these are a set of rules that define like natural numbers. Positive integers, cardinal numbers, ordinal numbers, call them what you are. We use them to count. And so I think there are like a dozen key axioms, but they can all basically be boiled down to 0 is a natural number, and every natural number has a number that comes after it. So you can think of numbers not as 1, 2, 3, 4, but as 0, and the one that comes after that, and the one that comes after that, and the one that comes after that. So back to numbers. If you're wondering where we went with that little tangent on P&O axioms, it's because we're going to talk about church numerals. This is named after Alonzo Church. He was Alan Turing's doctoral advisor at Princeton. He actually advised a lot of really famous, foundational computer scientists and mathematicians. So when you think of counting, basically, you don't really use numbers apart from counting to things. And so there isn't anything like inherently great about the number 5, except that it's like, one more than 4, right? Or it's the number that your product manager asked you to put items on the page. But anyways, you keep iterating, and that's really what you use numbers for, is iteration. So we can define 0 as basically a function that takes a function and like a 0 value, and it just returns the 0 value. So it's like, don't do anything with that function, just return whatever was passed in. And then its successor can be defined as a function that takes a number and then returns a number that actually just applies that function to the number. So this is actually a lot like reduce. It'll make more sense. So you can think of 1 as the successor of 0, 2 as the successor of 1, and so on. So you can convert back to native numbers in JavaScript by basically passing a function that adds 1 to whatever it takes, and then 0. So if you convert 0, it'll skip this function and it'll just return 0. Otherwise, with 1, it'll pass in 0, it'll add 1 to that, and then return 1. And you just keep wrapping it, and it'll keep unwrapping itself like an onion. Does that make sense? Okay, cool. So because we know that the function isn't called for the case of 0, this makes it very convenient to check for 0, because we can just pass in true and then have a function that returns false if it's ever called. And so if you pass in 0, it'll always return true. And if you pass in anything that iterates, it'll always return false. So given that we have represented numbers with functions, we can actually add those, because we're already iterating, right? And what is math, or what is arithmetic except for like iterating? I'm sure a mathematician would disagree, but we're simplifying things. So basically, addition is just do something n times and then do something m times. And then multiplication is like do something n times, but every time do m. You guys know arithmetic, right? Like, we're all adults. Yeah, so if you think about successor, we already have a function that adds 1. So we can tweak that slightly to basically take 2 numbers and then do f n times and then do it m times. So you can add 1 and 3 and then convert that back to a number, and you'll get 4. This shouldn't be like surprising that like addition is a thing. But then if you want to multiply, we can tweak it so that basically you can apply m to the function and then do that n times. So you're just wrapping. And so this is all valid JavaScript. You can follow along. And then we can add one more definition. So subtraction is basically n's predecessor m times, right? But we haven't talked about finding a predecessor. P&O axioms don't really define a predecessor because everything starts at 0 and goes up. But we can basically add an axiom that says 0 is its own predecessor, and every natural number has a predecessor, right? So 4 is the successor of 3, but it's also the predecessor of 5. Or yes, 5. And so this is sort of complicated. I didn't actually derive this. I took this from Matt Might's blog. He's a professor at University of Utah, very smart guy. But basically, this will take a number and return the function that represents the number before it. And then when you want to subtract 2, you basically just have this predecessor function, and you pass it to m, and then pass that to n. So the predecessor of 3 is 2, and then if you subtract 4 or subtract 3 from 4, that's 1. Not surprising, but you're following along. OK, so if we want to write code without any keywords, then we can basically define block scope and take all these parameters, define them down below, and then some of these functions depend on functions that we've already defined. So you can't really do is 0 until you have true or false. Like one depends on the other. And then once you execute all of this, you can say like if 1 is 0, then ask why, otherwise send help. And this definitely asks for you to send help. But so you noticed everything here is anonymous, right? Nothing can name itself, which is a problem because they can't call themselves. So you can't have a function that is totally anonymous, that is unnamed, that also somehow knows how to name itself and then call itself, right? Years ago, this is sort of based on the lambda calculus, which was developed like in the 20s and 30s. And it was meant to be a system of representing formal logic. They wanted to perform proofs in the lambda calculus. And so in order to do that, they really needed to make sure that it was tried and true and tested and that it works. And it turns out that they found a paradox in the lambda calculus that you actually can self-reference anonymously. And it was actually a huge controversy at the time. It started with the U combinator because this is very simple. You can wrap a function in a function and then just pass it to itself. And so you might have a function add that takes a parameter called add. And that might not be useful because you would want to probably add and not just call yourself. But you can. So they created, so I won't go too far into the Y Combinator because it is probably one of the most beaten to death proved things in math and computer science. But basically what they want to do is have a function that takes a function that when it keeps calling itself, it doesn't return new values. So if you keep like wrapping the output and sending it back through, you get like a fixed point. It won't fluctuate. So when this function matches that requirement, it's got a huge problem because it immediately calls itself and doesn't stop until your program dies. So you can add a little bit of indirection so that it doesn't immediately call itself. It returns a function that takes a function. And so basically, you can expand that out, and then you can't have y in the definition because it needs to be anonymous, right? You can't know your own name. So using the U combinator, they basically came up with this function that says you can wrap a function in this, and it will pass in the function so that you can call itself. And that will make more sense in just a second. Because we can put it all together. And so this you've seen before, like the is 0. But up here, we take a function called factorial. And so factorial is passed in, and it is defined as the Y combinator wrapping a function factorial, or a parameter factorial, and a parameter n. And if n is 0, then return 1. Otherwise, multiply n by the factorial of n's predecessor, right? We all know. And then at the very end, just pass in this little number back to the native number, and then call factorial of 5 and native. Does anybody know what factorial 5 is off the top of your head? Because it is 120. That is code without keywords. There's some further reading on this. The fixed point combinator you can look up on Wikipedia. Matt Might wrote a really, really good blog post that I used a lot of his code but upgraded to ES6. I wrote a little blog post about this. And then you can find all the slides here and follow me on Twitter. Yeah. Cool. It's a real website. I promise.
So Sam, do you mind answering a few questions?
I would love to answer questions.
So if anyone asks a question, do you mind repeating it so we can get on the video?
Yeah, definitely. Okay.
Awesome. I have 2 questions. Is that all right?
Yeah.
All right. So
Okay.
first one, do you have all the editions of structured interpretation of computer programs?
I own none of them.
You should get that book.
I know.
This would be perfect.
I know. Yeah. Someone actually told me yesterday that Jerry Sussman and Hal Abelman did this in a talk, and I
It's amazing.
didn't know it existed.
It's very similar to what you're doing. It's
Okay.
great. And also, second thing, if you implement double as a function, you can make your multiplication function logging time instead of n time, because you're doubling each time when it's an even number, and then subtracting when it's an odd on your iteration.
Oh. Okay. That's a good idea. Yeah. Performance here, by the way, you are you are adding in linear time.
Oh, yeah.
So yeah, don't do this. Trotter.
That was my question. I was going to say this looks really good for job security, but I'm wondering.
Right. Why would it be good for job security? I'd fire anybody who wrote that code.
By the time you really did it.
Yeah.
How do you maintain that without them?
Yeah.
Put your thing under a paddle.
Did you have a question, or was that?
Yeah, well, it's kind of also kind of a two-parter. This is a for fun thing, right? This is not really.
Oh yeah, no, really, don't do this. Understand how it works and know that it's possible, but don't do this at home, but not at work. Right.
The second thing, I think there was an error in the program on the previous slide.
Was there?
So.
Here?
Yes.
Because it ran.
Right, no. It's an error in that you cheated a little.
Morality.
I'm not sure. In line 12, do you not have to use
The plus, you mean? Is
yeah,
that
the x plus
the
1?
plus?
Don't you have to do suck of 1 or something?
No. So this is being passed in as my function native. And so you compute factorial of 5, and then you convert it to a native function and return that. And so that's how we get 120 at the bottom. Otherwise, you would wind up with a huge function that nobody understands and would be very difficult for me to tell you all is 120.
I think he's saying the x plus 1, though.
Yeah, isn't that
using your
You're using real life numbers, not your.
But yeah, but that's
Right, but
basically
that's
saying,
to
hey, I'm leaving the world of no keywords, and I'm going to native JavaScript land for this moment.
Yeah. Yeah. That's
To be fair though, you could have implemented this as a subsequent calls to successor in which you printed one, the word 1 up to the word 120 or something, and then didn't have to use any keywords. I was just gonna throw that out.
that's
Oh, I see. That turns it into actually the number 120.
yeah. And so that's how we get a result and not just
120 times. Right?
right. Yes. Are there any other questions?
Awesome.
Okay, cool. I hope you had fun.